Hi, and welcome to day 30 of Just Start Programming, the Rust programming language. I would like to congratulate you. So, if you have made it this far since day one, it was never easy, as this takes a lot of patience and perseverance to continue. So, let's get on with asynchronous programming, applying concurrency with async. Yes. So join me once again live in one take, no shortcuts, no secrets. So let's just start programming. All right. So here we are once again. Let's do a quick review, recap on futures and async syntax. So it's just to refresh our memory. Future trait. Okay. So future is a value that may not be ready now, but will become ready at some point in the future. And then you have the future trait. It's a building block. In Rust, futures are types that implement future trait. Each future holds its own information about the progress that has been made and what ready means. And then you have this async keyword to block, keyword to blocks and functions to specify that they can be interrupted and resumed. Within a sync block or a sync function, you can use await keyword to await a future, that is, wait for it to become ready. At any point where you await a future with a sync block or function is a potential spot for the sync block or function to pause and resume. Process of checking with a future to see if its value is available yet is called polling. Okay. So we did our first async program yesterday, and we made use of TRPL, or the Rust programming language. So this one re-exports all the types, traits, functions you need primarily from futures and Tokyo crates. So the futures crate is an official home Rust experimentation for async code. Okay, we created a project called Hello Async yesterday, and then we had this sample. Async. Okay, so this one gets a URL. So there's a URL endpoint, and it calls await. And once it returns something, response text await, then it will be it will check for the title and the title element, map title element, inner HTML. So it extracts the title. Yeah, so this one is an explanation where okay, this is another way of doing it in one line. So, you can cascade. Oh no, what not cascade, but chain. So this is another way of doing it. Writing async function is equivalent to writing a function that returns a feature. So here it's an async function. Another way of doing it is you have a function that returns a feature. And then you have async move here. Async move. Okay. The new function body is an async move block because of how it uses the URL parameter. So async versus async move later in this chapter. Determining a single page title here. So this one not compile, mainly because this one main function is not allowed to be async. So this is an exception. Main function cannot be async. And then the reason main can't be marked async is because it needs a runtime. So here we don't see any runtime, but in the next example here you have tprl run. So this is the runtime. When we run this code, we get the behavior we expected initially. Okay. Each wait point, that is every place where the code uses a wait keyword, represents a place where control is handed back to the runtime. To make that work, Rust needs to keep track of the state. This one, enum, I don't think we use this in the code. Partial, yeah, so we did not use it in the code. Let me check. Okay, so no, we did not use it. Okay, then we try this one, racing our two URLs against each other. So there are two page title that is being processed. The function here is an async function. And then here there's a tuple, and then this race executes either the one on the left or the one on the right, whichever comes first. Okay, this one is called over here, and then in this function, if title future one finishes first, then left will be returned, and then it will print the URL here. URL return first. Match maybe title, some title. If there's a title, then its page title is displayed. If there's no title, then its title could not be parsed. So we tried this yesterday, and here you may discover that some sites are consistently faster than others. So it depends. So we played around different sites yesterday. Okay, but based on results, which one usually returns first? Grades.io return first. Or was it Ryan? I think most of the time Ryan was the winner. Okay, so let's move on to the next topic, which is applying concurrency with async. Okay, applying concurrency with async. In this section, we'll apply async to some of the same concurrency challenges we tackled with threads in chapter 16, because we already talked about a lot of the key ideas there. In this section, we'll focus on what's different between threads and features. In many cases, the APIs for working with concurrency using async are very similar to those for using threads. In other cases, they end up being quite different. Even when the APIs look similar between threads and async, they often have different behavior. And they nearly always have different performance characteristics. Creating a new task with spawn task. The first operation we tackled in creating a new thread with spawn was counting up on two separate threads. Let's do the same using async. The trpl create supplies a spawn task function that looks very similar to the thread spawn API, and a sleep function that is an async version of thread sleep API. We can use this together to implement the counting example as shown in listing 17-6. Okay, so here we have duration, function main, the Rust programming language, create library. You have run, so this is the scope of the runtime. Async on this scope, and then we are calling spawn task. And then there's another async. Async scope here. Yeah, so this one. And then you have the for loop I in 1 to 10. Print line high number. Okay, so it depends on the value of I from the first task. And then there's a sleep duration from millis, 500 milliseconds, and then there's a wait. And then here, after spawning 9 to 10 minus 1, 9 threads. Is it threads? Oh, it looks similar to thread spawn. Okay, so threads. Then this one will count I in 1 to 5, high number I from second task, duration from millis 500, await. Okay, so let's check if we have it here in the code. Okay, so it's not here. Let's copy this. We can reuse this code. Put it here. Let's comment out this part. Duration. There's something wrong with the code. Main. Okay, we can remove this part. Okay. Let's run this. Okay, so what happened here? Okay, number 1 from second task, number 1 from first task, 2 from second task, 2 from first task, 3 from first, 3 from second, 4 from first, 4 from second, 5 from first. So it stopped at 5. 5 from first task. Okay, so let's check. 5 from first task. Okay, this one is actually 1 to 4. So second task, because it reached 4 from second task, then it stops. Okay, so let's see the explanation here. As our starting point, we set up our main function with trpl run, so that our top level function can be async. So async function enclosed in a runtime. From this point forward in the chapter, where every example we include this exact wrapping code with trpl run in main. So we'll often skip it just as we do with main. Don't forget to include it in your code. Okay, so we need to remember. We need to have this. Then we write 2 loops within that block, each containing sleep for half a second, 500 milliseconds, before sending the next message. We put 1 loop in the body of trpl spawn task and the other in a top level for loop. We also add an await after the sleep calls. Okay. This code behaves similarly to the thread-based implementation, including the fact that you may see the messages appear in different order in your own terminal when you run it. Okay. So it doesn't have to be in exact order, like first, second, first, second. But the important point here is when the second, was it second task? Yeah, so it should be the second task. When it reaches 4, then it will stop. So it will not be spawning any thread. So this version stops as soon as the for loop in the body of the main async block finishes, because a task spawned by spawn task is shut down when the main function ends. If you want it to run all the way to the task completion, you will need to use a join handle to wait for the first task to complete. With threads, we use the join method to block until the thread was done running. In listing 17-7, we can use wait to do the same thing because the task handle itself is a feature. Its output type is a result. So we also unwrap it after awaiting it. Okay. So here, the usual approach is to have a join handle. In this example, we can use a wait. That sounds interesting. Let's see. How can we use a wait? Here. Handle await unwrap. The other day, I think it was handle.join was in handle.join. Let's just check once again. Was it from here? No, I think it's over here. Handle.join. Okay, from thread spawn. Handle.join. However, over here it's handle await. Okay, we can try this one. Let's copy this. Should be after this one. Handle await. Cannot find value handle. Okay, here we need to add handle. That handle equals handle. This one returns join handle. Okay, so because it returns join handle, but this one calls await. So let's see. Four from second task is done. Okay, number 5 from first task still continues, and then it terminates. Can we do the usual one? Can I put in handle dot join? Do we have that? No? Okay, we don't have it. It's not here. What was the handle last time? Here it was thread spawn handle push. This is a thread spawn. Okay, but this handle is spawn task. Spawn task returns join handle. So join handle. We just try let h equals trpl spawn. Oh, not spawn, but not trpl. Let's say thread spawn. This is also a join. This is a join handle. What's the difference here? What's the difference? Spawn task, you have a future, it returns handle, join handle. Thread spawn, it also returns join handle. Join handle. Cancel. What did I miss? Thread spawn handle. std thread, standard thread. Okay, so this one doesn't use TPRL. Handle join. Should be handle at join. Let's try H. Join. Okay, join is here. I can do that. This one. So join handle. Which join handle is this? I think it's a different join handle. Okay, so it's a different join handle. Doesn't have handle that join. Let's verify once again. Handle that join. Okay. Alright, so let's remove this one. Let's put it back. Okay, and then this one we can remove. Okay, let's continue. This updated version runs until both loops finish. Yeah, 1 to 5 from second task, or not 1 to 5, but 1 to 4. So 5 minus 1, 4. Then from the first task, that is 10 minus 1. So that's why we see 9 here. So far it looks like async and threads give us the same basic outcomes, just with different syntax using await instead of calling join on the join handle and awaiting the sleep calls. The bigger difference is that we didn't need to spawn another operating system thread to do this. In fact, we don't even need to spawn a task here, because async blocks compile to anonymous features. We can put each loop in an async block and have the runtime run them both to completion using join function. There's the join function. We can put each loop in a sync block and have the runtime run them both to completion using trpl join function. Okay, let's see. Future one. Okay, here in the section waiting for all threads to finish using join handles. We showed how to use the join method on join handle type return when you call std thread spawn. Yeah, this is from the previous sample code. The TRPL join function is similar but for futures. When you give it two futures, okay, so there's also a TRPL join. When you give it two futures, it produces a single new future. Its output is a tuple containing the output of each future you passed in once they both complete. Future 1, future 2. So the return will be a tuple of future 1 and future 2, I assume. When you give it two futures, it produces a single new future whose output is a tuple containing the output of each future you passed in once they both complete. Once they both complete, meaning because of the join and await. Okay, we use TRPL join to wait for both future 1 and future 2 to finish. We do not await future 1 and future 2, but instead the new feature. Okay, so there will be a new feature that will be returned, and that's where we use await. We ignore the output because it's just a tuple containing two unit values. When we run this, we see both futures run to completion. Okay, so let's try this one. Wait is used in non-async function. Non-async. Okay, so we forgot this part. Okay. And then let's run it. We should see 1 to 9 and 1 to 4. Okay. So the second task should be 1 to 4. Then the first task is 1 to 9. First task 5, 6, 7, 8, 9. Okay. Let's read the explanation. Now you'll see the exact same order every time, which is very different from what we saw with threads. That is because the TRPL join function is function is fair, meaning it checks each future equally, often alternating between them, and never lets one race ahead if the other is ready. With threads, the operating system decides which thread to check and how long to let it run. So I think that's the major difference. Threads, the operating system decides, but with this one, join each future equally alternating between them. Never lets one race ahead if the other is ready. With async rust, the runtime decides which task to check. In practice, the details get complicated because an async runtime might use operating system threads under the hood as part of how it manages concurrency. So guaranteeing fairness can be more work for runtime, but it's still possible. Runtimes don't have to guarantee fairness for any given operation. They often offer different APIs to let you choose whether or not you want fairness. Try some of these variations on awaiting the futures and see what they do. Remove the async block from around either or both the loops. Await each async block immediately after defining it. Wrap only the first loop in a sync block and await the resulting future after the body of the second loop. For an extra challenge, see if you can figure out what the output will be in each case before running the code. Okay. So a chance for us to try something out. Okay, so the first one, remove the async block from around either or both the loops. Okay. Where is it? So there's a sync block here, sync block here. First, but if we remove the async block, then we don't have a future. Okay, so let's try to remove that one. Future, so there's no future one. What will happen? Yeah, there's no future one. Okay, we remove future one here. Like this. We cannot do a join. Argument 2 is missing. So we cannot do something like that. So we don't want to join. It's just that this one will run and this one will run in this async. Okay, so let's guess which one, what is the output. So here, this is the overall async. This one will start with 1, then it will sleep. So I think it will try to finish 1 to 9, and then we see something here. Because this one is not in its own async. Okay, let's try. First task, yeah, 1 to 9. Oh, and then it stopped. Hi, number 1 to 9, first task. So it just did this part. Is it because How should we interpret this? 1 to 9, this one executes and it finishes. So the entire runtime is already complete. Okay, let's try if I uncomment this one, comment out. So 1 to 5 will be executed basing on what was the output from the previous one. Let's see. 1 to 4. Yeah, so 1 to 4 got executed. Okay, so we removed the async both ends from here and also here. So what is it that we wanted to try now? Await each async block immediately after defining it. Okay, so let's put this back. Let's put this back. Then feature 1 await. Let's run first task. So it stopped. It stopped. Await a feature will suspend the current function's execution until the executor has run the feature to completion. Okay, so it will disregard this. And if we comment out this one, here, feature 2 await. Now, if we put it here, it will be 1 to 4, but it will also include this part. Oh, I was wrong. So it will only run this part here. Okay, so how about if we do for both? So if you do for both, it will execute feature 1 first, and then you'll execute feature 2. So by having await, it seems like this is done in sequence now. First, and then here, this is done, then it will proceed with this one. If we comment out both, so 1 to 4, this one would be, it could be that 5 will show up. Let's run. Right. Oh, having future 1 await and future 2 await is similar to this one. First, second, first, second, first, second, first, second, first, second. Then 5 to 9 is from the first task. So they're not the same. Not the same. You do it like this. Nothing was. The one inside was not called. Okay, so it means that if I uncomment this one, what happened was executes this, but this one was not executed, just like when we had for both. Let's run it again. Yeah, so the first task was the only one that was executed. Here, because the future 2 was not used, but if we add in this one, future 208, so 1 to 4, but will it execute this? From 1 to 9? I don't know. Let's see. 2, 3, 4, 5, 6, 7, 8, 9. So it did execute it. This was executed. Feature 208. This one was also executed. Okay, so let's read and see. Wrap only await each async block immediately after defining it. We did that. Wrap only the first loop in an async block and await the resulting future after the body of the second loop. Yeah, so that's what we did. So it executed this and then this one because we have the await. Without future to await, if we remove this, this one will be executed. If we have this async and we don't put in the await, it will not be executed. Suspend execution until the result of a future is ready. So if we don't have await, what does async do? Turn the marked code into a future. As such, the code will not be run immediately, but will only be evaluated when the return future is that awaited. Okay, so that's why it did not execute if we don't have the await. It will, but will only be evaluated when the return future is not awaited. So that's why if we have this and we remove all await, so the behavior is that it's not executed at all, mainly because it was not evaluated. So it's necessary to have the await here. Okay, let's see. So it did not count up the number. Okay, so either of this, if you put await, so this one will be evaluated, this one will not be evaluated. And again, yep. Only 1 to 9 was executed. Mainly because when you put async here, you need to put await. If we remove async, we remove this one will run. Okay, so let's save it. Having this feature 1 await, feature 2 await, so that we'll see the output. Okay, let's move on. Counting up on 2 tasks using message passing. Sharing data between future will also be familiar. We'll use message passing again, but this time with async versions of the types and functions. We'll take a slightly different path than we did in using message passing to transfer between threads. To illustrate some of the key differences between thread-based and future-based concurrency, we'll begin with just a single async block, not spawning a separate task as we spawned a separate thread. Okay, so let's try to implement this one. Copy, and here we'll comment out this part. So we need to copy this part. Then we need to enclose it in sync. Future, okay, async run. Let's execute this. Got hi. Okay, so what's going on here? We have async, then we're using a channel. Transmit and receive. So let val string to contain hi, and then in transmit we send the value, then unwrap. Then here receive rx receive dot await unwrap. Oh, okay. So there will be this channel. There's this channel where once it receives something, then it will print. I think that's the basic understanding here. Let's see what's in the explanation. Here we use the TRPL channel An async version of the multiple producer single consumer channel API we used with threads back in chapter 16. The async version of the API is only a little different from the thread-based version. It uses a mutable rather than immutable receiver, Rx. Okay, so mutable Rx. Mut is here for mutable. And its receive method produces a future we need to await rather than producing the value directly. Now we can send messages from the sender to the receiver. Notice that we don't have to spawn. Okay, so here we don't have to spawn a separate thread or even a task. We merely need to await our X receive call. Await. Okay, the synchronous receiver method in MPSC channel blocks until it receives a message. TRPL receiver does not, because it's a sync. Oh, okay. TRPL receiver method does not, because it's a sync. Instead of blocking, it hands control back to the runtime until either a message is received or the send side of the channel closes. By contrast, we don't await the send call. Okay, so here we don't await the send call because it doesn't block. Send doesn't block. It doesn't need to because the channel we're sending it into is unbounded. Okay. But receive needs to await. If it's ready, then it will print this one. Note, because all of this async code runs in an async block, TRPL runtime call, everything within it can avoid blocking. However, code outside it will block on the run function returning. That's the whole point of the TRPL run function. It lets you choose where to block on some set of async code, and thus where to transition between sync and async code. In most async runtimes, run is actually named block on for exactly this reason. Then when we see run, we interpret it as block on. Okay, here, block on. This one. So does it mean that if we print here, it will not print here until we got something. Let's see. Yeah, so got is printed first, and then you have here. Run is interpreted as block on for exactly. Okay. Notice two things about this example. First, the message will arrive right away. Second, although we use a future here, there's no concurrency yet. Everything in the listing happens in sequence, just as it would if there were no futures involved. Let's address this first part by sending a series of messages and sleeping in between them, as shown in 17-10. Okay, what has changed? Okay, so we implement it this way. Keep run and then tx, where is tx? Oh, I commented out this part, so let's make it back. So here we have a vector macro line from the future. Okay, val. For val in vals, transmit, send, val, unwrap. Then we will sleep for 500 milliseconds and then await. We're here while let sum. Okay, let sum. Value receive. Wait. Why do we have that sum here? Because of option. Option. Okay, so let's run this. I from the future. Is it still building? What? It's still building. Okay. It did not terminate for some reason. Why? Sending and receiving multiple messages over the async channel and sleeping with an await between each message. In addition to sending the messages, we need to receive them. In this case, because we know how many messages are coming in, we could do that manually by calling receive await 4 times. In the real world, though, we'll generally be waiting on some unknown number of messages, so we need to keep waiting until we determine that there are no more messages. We know that there are no more messages. Listing 16-10 used a for loop process all the items received from synchronous channel. 16-10, okay, that was in the previous example. Rust doesn't yet have a way to write a for loop over an asynchronous series of items. However, so we need to use a loop we haven't seen before, the while let conditional loop. This loop version of the if let construct we saw back in concise control flow with if let and let else. The loop will continue executing as long as a pattern it specifies continues to match the value. The Rx receive call produces a future which we await. The runtime will pause the future until it is ready. Once a message arrives, the future will resolve to some message as many times as the message arrives. When the channel closes, regardless of whether any message have arrived, the future will instead resolve to none to indicate that there are no more values and thus we should stop polling. That is, stop awaiting. The while let loop pulls all of this together. If the result of the calling receive await is some message, we get access to the message and we can use it in the loop path as we could with if let. If the result is none, the loop ends. Every time the loop completes, it hits the await point again. So the runtime pauses it again until another message arrives. The code now successfully sends and receives all of the messages. Fortunately, there is still a couple of problems. For one thing, the messages do not arrive at half-second intervals. They arrive all at once, 2 seconds, after we start the program. For another, this program never exists. Instead, it waits forever for new, So it waits forever for new messages. You'll need to, so you will need to shut it down using Control C. That's what we did. Let's start by examining why the message come in all at once after the full delay, rather than coming in with delays between each one. Within a given async block, the order in which await keywords appear in the code is also the order in which they're executed when the program runs. There's only one async block, so everything in it runs linearly. There's still no concurrency. All the transmit send calls happen interspersed with all of the sleep calls and their associated await points. Only then does the while let loop get to go through any of the await points on the receive calls. To get the behavior we want where the sleep delay happens between each message, we need to put transmit receive operations in their own async block. Okay, as shown in 17-11. So async and async. This is for receive, this is for transmit. If we awaited the individual features in sequence, we would just end up back in the sequential flow. Okay, if we awaited the individual features in sequence, so that's by putting tx fut that await here, and then tx rx fut await here, so it will be in sequence. Okay, but we don't want the sequential flow. Okay, and in this case, join is used. RPL join on tx fut and rx fut. Then you have await. Separating send and receive into their own async blocks and awaiting the features for those blocks. With the updated code, the message get printed 500 millisecond intervals rather than all in a rush after 2 seconds. Okay, first, let's do this again. Let's run this code. Building. Okay. From the future, and this one will keep on running. So we need to press Control C to terminate it. Next, we need to enclose them in a sync block. So let me just copy this so that it's much faster. Anyway, we already know it's to be done there. And here, let me comment this out once again. So we'll keep the runtime. Here we have async. It's the scope of async. This part. And then here, the scope is also here. Then we do a join. So let's run this. I'm from the future. Okay, so now it's in every half a second. But this one did not terminate. Why? Is it because of this? While that's some. Let's see how we can terminate that. With the updated code in 17-11, the message get printed have this is 500 milliseconds. The program still never exists, though, because the way the while let loop interacts with TRPL join. The future return from TRPL join completes only once both futures passed to it have completed. Oh. Okay, so it did not complete because this one is still running. But while let some, you have some value. After this, you have none. Okay, so the TX feature completes once it finishes sleeping after sending the last message in pass. The RX feature won't complete. Yeah, it won't complete until the while loop ends. The while let loop won't end until awaiting RX receive produces none. But when will it produce none? Awaiting RX receive will return none only once the other end of the channel is closed. The channel will close only if we call receive close or when the sender side TX is dropped. We don't call RX close anywhere and TX won't be dropped until the outermost async block pass to TRPL run ends. The block can't end because it's blocked on join completing, which takes us back to the top of this list. Okay, so that would explain it. We could manually close RX by calling RX close somewhere, but that doesn't make much sense. Stopping after handling some arbitrary number of messages would make the program shut down, but we could miss messages. We need some other way to make sure that TX gets dropped before the end of the function. Right now, the async block where we send the messages only borrows TX because sending a message doesn't require ownership. But if we could move, okay, so I think that's the hint. But you could move TX into that async block, it would be dropped once that block ends. In chapter 13, capturing references or moving ownership, we learned how to use move keyword with closures. And as discussed in chapter 16, using move closure with threads, you often need to move data into closures when working with threads. The same basic dynamics apply to async blocks. So the move keyword works with async blocks just as it does with closures. Okay, in listing 17-12, we change the block use to send message from async to async move. Async move. Okay, then this one will be dropped after it finishes vals, after it finishes this. And then we will receive none. And then, yeah, so that will complete it. When we run this version of the code, it shuts down gracefully after the last message is sent and received. Oh, I'm only doing this. Move. Move, so the concept of borrowing. used here. Okay, so let's try. We only need to make this async do a move. So that it will terminate after this. It will be dropped. Let's run. Fly from the future. Ah, it worked. It worked. Let's sum. Yeah. So it terminated, and then since it was dropped, it's no longer sum. So the loop terminates. Let's try the Rx close also. So I'll remove the move here, and then after getting one value, let's just do an Rx dot close. Doesn't make sense, but it will receive one value, so this one will terminate. And then it will stop. Okay, let's run this. Oh, terminated. Somehow it panicked. Send error. Yeah, it panicked. Interesting. Okay, so I cannot do it that way. The async channel is also a multiple producer channel, so we can call clone on TX if we want to send message from multiple futures. Multiple futures. Okay, TX1, TX clone, TX future. Okay, so where is TX1 called? This is TX future, TX future. Okay, here the channel is a clone, TX1. This part. So this part is using the clone, and this part is using TX, original TX. Okay. And then we have a join TX1 future, TX future, and RX future. First, we clone TX, creating a TX1 outside the first async block. We move TX1 into the block just as we did before with TX. Yeah, here, move. And then there's move also here. Okay. Then later we move the original TX into a new async block where we send more messages on a slightly slower delay. We happen to put this new async block after the async after the async block for receiving messages, but it could go before it as well. The key is the order in which the features are awaited, not in which they are created. Yeah, I think we have seen this previously. Both of the async blocks for sending messages need to be async move blocks so that both tx and tx1 get dropped when those blocks finish. Otherwise, you'll end up back in the same infinite loop we started out in. Finally, we switch from trpl join to join is only for 2 and this one is for 3. I did not notice that there's 3 here to handle the additional feature. Now we see all the messages from both sending features, and because the sending features use slightly different delays for sending, the messages are also received at those different intervals. This is a good start, but it limits us to just a handful of features with 2 join or 3 join 3. Let's see how we might work with more features. Okay. Let's try to copy this first. Okay. So we know that we need to enclose it in the runtime. What did I miss? Different indentation. Because it's already here. Or I can remove that. Sessional. Different. Async. Okay, async. All the way here. That is wrong. That one. Okay. There. Okay. Then let's run this. More from. Yeah. So this one will not have that order. Hi from the future. Then more messages for you. Hi from the future. More messages for you here. Yeah, so here we are limited to only 3 features. So this is, I think this is only for illustration purposes, so that we would understand that, yeah, we are combining this feature, and after the 3 finishes, then it can move on to the next line. Okay, so let's see, we've done that. Yeah, so this is a good start, and I think we have reached the end of the topic. Let's take a quick peek at the next one. Working with any number of features. Here. So there's this function, join macro. Okay, so we will try that one out tomorrow or the next day. So I hope I see you guys tomorrow and you can join me. Yeah. So once again, thank you so much for finally making it to the 30th day. Although for me it's not exactly 1 month. Yeah, but for me 30 days is spread across I think I started 28th of June, so it's already 7th of August. Yeah, so there are times in between where I skipped, but when I skipped, I really did not touch on Rust, as you can see here, because this is live. So I'm new to Rust once again. So this is also to simulate how would one learn Rust. I'm just allocating maybe 1.5 hours now every day. Unlike in the uh, early videos where I just go on and on, but spending 1.5 hours a day is not that painful, I would say. Yeah, we just need to persevere and push forward. All right, so I don't know how many days exactly we'll reach at the end of the book, but I have plans doing this cover to cover and see what we can learn from this book itself. All right, hope to see you guys tomorrow. And before I finally end, let me thank my sponsors. Or not sponsors, but supporters.